Okay, let's do the final question of 2013 here. This diagram shows a simple circuit that can be used to charge a capacitor. So there's no discharge in this circuit. Redraw the circuit in the space below. Add an ammeter and a voltmeter into the circuit so the readings of the current through the capacitor and voltage across the capacitor can be measured. So we draw our power supply, we draw our switch, we draw our capacitor, and what we need to do is put in an ammeter in that series circuit anywhere. Now, it's probably good putting it next to the capacitor, but it doesn't really matter where we do that. We can do it anywhere. And then we need to add a voltmeter across the capacitor. And I mean, even look at the word voltage across, not through. So we need to put a voltmeter across the capacitor. Now it can be up or down, doesn't matter if you do it in here or down here. I'm going to do it here. One connection before the capacitor and one after. Okay. How will the voltage change as the capacitor charges? The voltage will go something like that. Okay, so it will increase as it charges up because there's more charge on the capacitor, the voltage increases. However, it will increase sharply at first because it's easier to put more charge onto the capacitor initially when there's no charge on it. There's no voltage pushing back. And then it gets harder and harder, so the rate of increase decreases with time for the voltage. The current measures how much charge flows in the circuit. So at the start, it's quite high because there's a large amount of current flowing to put that large increase in charge and voltage onto the capacitor. But towards the end of this graph, you can see the voltage hardly changes. Therefore, the charge on the capacitor hardly changes. Therefore, there's very little charge flowing around the circuit. So it gets less with time, and it just follows our exponential decay curve. Okay. Now, it's hard taking those readings because if they change very, very fast, we can't really take the measurements quickly enough. It's hard to look at the timer you're using and then also read off, say, a digital ammeter or voltmeter that's changing rapidly. To make it change slowly, I would probably increase the resistance, or you could say increase the capacitance, because if you remember, our time constant is R times C. So if we increase any of those, the time that those changes happen over will increase, and it'll be easier to measure. Part B. An electronic flash for a camera produces a flash by using the energy stored in a 185 microfarad capacitor. The power output is 1.2 kilowatts, so that's by 10 to the 3 watts, and the duration is 0.8 milliseconds, so that is by 10 to the minus 3 seconds. The efficiency of the energy transfer from the capacitor to the flash is 76%. Calculate the initial charge stored on the capacitor. So this is the output power, but that's only 76% of the total power that was, or the energy or power that was available in the capacitor. So the total power on the capacitor, or from the capacitor, times 0.76 times 76% equals 1.2 by 10 to the 3 watts. Therefore, the power that was available from the capacitor, had it been 100% efficient, would be 1.2 by 10 to the 3 divided by the 0.76, which gives us the power being well, not quite the right way of wording this, but that'll be 1.579 watts would have been the output from the capacitor itself. But it tells us that this was 0.8 by 10 to the minus 3 seconds. So we can do power is work done divided by time. Work done is power times time, which is 1.579 by 10 to the 3 multiplied by the 0.8 by 10 to the minus 3, which gives us 1.26 joules. Okay, so we need to calculate the energy first. Then we can use energy equals, and we're trying to find Q, and we've been given C. So the equation that we should use is a half Q squared all over C. It's very rare we use that one actually. So we can put in our values. 1.26 equals 0.5 times Q squared over our capacitance, which is 185 by 10 to the minus 6. 1.26 divided by 0.5 multiplied by 185 by 10 to the 6 equals Q squared, which gives Q squared as being minus 6 in there. 4.662 by 10 to the minus 4. Just taking the square root of that then gives us 0.0216 or 0.0022, depending on how many significant figures you give it to. Okay.